Before I start the lecture tonight, first I would like to announce the the midterm. So after consultancy with the department, there is no late for the midterm. So that means we don't need to have midterm, but then I will assign you more assignments, and as the proportion of the assignment. So that means right now, maybe every 3 weeks, I will give you one assignment. But the total score would be the just like what we announced. So later, I will give you a new announcement about the assessment. Okay. Yeah, thank you, guys. Okay, so let's try to finish what we started last week. About the statistic parts. So right now we go to the center. Here we try to have several things. First of all, the general concepts, and then we will particularly go to 3 parts, like the confidence interval, decision theory, and also like the hypothesis test. Yeah, 3 parts. So first of all, for what are statistics, last week I mentioned we should have a population. So for here, when we mention the population, it means we will have some underlying. Yeah, so here you may say underlying distribution, we just say underlying mechanism, right? But for such mechanism, you would say this is a probabilistic. Yeah, this would be some probabilistic distribution or some other things. Yeah, so this population, and then it comes out the parameter. So for parameter here, you may consider this is a numerical measurement describing the characteristics of a population. So here you may consider 2 different situations. The first one, if is a exactly parametric. Yeah, in such a way, that means you actually have a distribution already. Here you know the functional form. However, here you will have some unknown parameters. So in this way, you just try to, for example, if you are given a random sample, x1 to xn, and we know it would follow such kind of distribution, and then you derive the theta, right? So this is parametric. But in some situation, we call it the wrong parametric. Yeah, for some wrong parametric situation, that means here for your fx, the functional form is actually unknown. Yeah, this is unknown, then you need some ways to estimate it. Yeah, for example, you use some color smoothing to estimate. Yeah, this is a very typical long parametric estimation methods. And nowadays, you also have some other ways. For example, if some fx is unknown, you may consider like possibly CNN, DNN, RNN, or even like a vision transformer. Yeah. So this is the one. Next one about the sample. So for sample, like I just write here, yeah, you have a x1 to xd and IID from fx. So here for x1 to xn, we just call them the random sample. Yeah. So in some small sample situation, so we call this one random sample. And then we know for every xi, the distribution is the same. And for each of them, they would be uncorrelated or independent. Yeah. So this is the sample. And then for statistic, last week we mentioned roughly you may understand it as what? As a function with respect to your random sample. So that is here. For your sample here, yeah, you see this one? Yeah, I may just denote by x. So here x is a random vector. So for such a random vector, then you know it contains n different entries. Yeah. So here for statistic, we just know it should contain no unknown parameters. Yeah, last week we mentioned. And here is the possible relationship between them. For population, that means this is the overall group, right? And then sample just means you find a subset, particularly if the population size, attention, the size, for example, if you have x1 to xn, so here n just means the sample size. Yeah, but in some situation, sample size has a special meaning, okay? Here, if the sample size is too large, you consider a subsample, and then we try to use the sample to estimate the parameter, and then such parameter, when you try to estimate it, you have to see whether it satisfies some properties. So in this way, you then try to have a statistic, and this one then just help. Okay, so number two, how do we obtain and sample data? So here we actually have two ways to collect data. So two ways to collect data. The first one, observational study. For observational study, the opposite one would be what? Would be experimental studies. So here, if you compare these two, observational, that means you observe, you collect, right? So this one just means collecting data by measuring characteristics without influencing the subjects or their environment. So that means for observational study, you have low intervention, right? No intervention on the data. And then, for example, you can track websites user behavior, right? Just like you collect during from Monday to Friday, you don't have the data. Yeah. And the advantage, just like it's easy to get the data and you have the minimal setup and you don't consider the ethical thing. Otherwise, yeah, later when we go to the next part, yeah, if you go to some experimental studies, so you have to be limited to ethicals. Yeah, so like you design and then you have to get a approval for some special things. Yeah, so goes back for observational study. Yeah, here advantage just like you require the minimum and easily to get data, but the limitation would be what? The data is restricted to naturally occurring behavior. Yeah, and it cannot, attention, it cannot induce or control a specific behavior. So in this way, there might be serious bias. Yeah, if happened, there would be something. Yeah, so observational study. Next one here. Why observational studies are needed? Number one, yeah, sometimes when you have to suffer from ethical or practical limits. So in this situation, to collect data of your interest is very hard. But if you have the observational study, then you pay less. Okay. The second one, if there the existing data like you what you need is very large, but if you through experiments, sometimes it's very hard to collect data. Yeah, for example, like my collaboration with eye specialists is like in many situations they told me, oh, Catherine, the sample size is too many. For example, even we collect 72 patients is so hard. Yeah, sometimes you see 72 seems like a small size, but hardly for doctors to collect those sample. So then they just rely on the statistician. So can you design special methods so that like your methods can make up the small sample size, right? So observational study can help. Yeah, and the real world context here, no intervention means data reflect natural condition, but it then beyond what you plan to explore. So next one, we go to experimental study. Here, for such kind of data collection methods, the treatment is applied to subjects called experimental units, and its effects are observed. So typically, such experimental units are divided into two. One is about the control group, and one is about the experimental group or treatment group. Yeah, treatment and control. And for such a situation, people would call it RCT, randomization clinical trial. So if your data is under some randomization clinical trial, that means your data can explain some causal relation. So that's why here we say experimental study to some extent is very important. However, it also suffers the problem, like here, you see the disadvantage, I guess, should be the next page. Oh, here was mentioned, but you can go to above. I mean, here is the one. I mean, if you have to suffer the ethical limits, right, and the cost is very expensive, then experimental design would be good. And here, attention for some RCT here for such a randomization. Let me explain these words. Randomization means words. Participants are randomly assigned into two groups. Treatment group receiving the new drug, control group receives placebo that is visually identical but contains no active gradient. So this one tells us if you use some RCT randomization clinical trials, this one will help balance demographic and health-related factors between the groups. And then here, attention, for such RCT, it has several characteristics. Number one is blinding, and particularly like sometimes is a single blind, double blind, 双盲 and single blind 单盲. Yeah. So blending is often employed to reduce for the purpose to reduce the bias. Single blind means only the participants do not know which group they are. For double blind, here neither participants nor the researcher know the group assignment. So this one would effectively, prevents expectation effects and the research bias. Yeah, this is some blending. And the next one I want to introduce is about usually such measurement would be a repeated measurement. So why is repeated? For example, if I just want to see like the biannual biannual effect. So every half year, I just visit you, so and then 1 year visit you again. So that means within 1 year, you only visited at most twice. And if unfortunately, when one visited you, you are lost there, right? You are absent, then there might be only one or even no. So for repeated measurements, one thing we just call it the longitudinal. Yeah. So longitudinal observation or longitudinal repeated. In such a way, we say the repeated measurement would be sparse. Yeah, so this is one. And another one just like dense. Another one just like dense. So in what kind of situation it would be dense, repeated measurement? It's actually everywhere, right? For example, for the Hansen index, every day you have Hansen index. And also like every minute you have the one. Yeah, so you can have the updates. Or just another thing, like if you have a climate station, so there every minute or every 10 minutes or every hour, so the station will record like the wind speed, like the humidity, the temperature, or everything, right? So here that means if 1 hour you observe, 24 hours you have 24 observation, and then 1 week you have 24 multiplied by 7, right? So in that way, the measurements repeated but dense. So here for dense or sparse, people would use different ways. For example, when it is sparse, so we say the longitudinal repeated measurements, then there would be something we call it longitudinal data analysis. And then for dense thing, that means you may consider like a functional data analysis or panel data analysis. Yeah. So here for repeated measurements, we don't know. And for RCT, here comes the advantage. It controls the placebo effects, reduce the bias, and increase results reliability. Okay, here comes one example like a control and the treatment. I just skip this one, okay? Next one, we may use a flow to show, or you may call this is a architecture. So look at here. At the very beginning, you have some experimental planning. Yeah, for example, here you would have some KPI. So you guys understand the KPI, right? Conversion rates, click-through rates, weight, etc. And then next one is about the level of significance. So what does this one mean? This one usually just means that some type 1 error probability. So this was just like the minimum detectable effects. The next one is about the statistical power. So statistical power, when we have this one, we have some specific formula. And usually if you can calculate a statistical power, that means what? Here you have the null volatility hypothesis. You must have this one, right? And then under the volatility hypothesis, you would have some distribution. And accordingly, you can calculate the confidence interval or just like the more things. Yeah. And then here you can calculate sample size. Yeah, here shows you. Yeah, you see, if you want to do statistical power, usually the formula would be what? Given H naught is 2, so that is, you must have a volatility hypothesis, and then you calculate the probability you reject the null hypothesis. This is the power. And also like the sample size, here for sample size calculation is one question. For our course, we do not ask you to calculate by hand, but we need you to read the code and output and then answer the question, give the formula. So for example, like here, if you have a two-polar Poisson z-test, and here you have the equally sample size for two groups, treatment and control, so here you would have some sample size calculation formula here. Yeah. Two peers I know, Professor Sao Jun from Wisconsin and Professor Hansong Wang from Peking University. So these two guys, Sao Jun, Professor Jun Sao is the supervisor or advisor of Professor Hansong Wang. So when Hansen was still a PhD student, so Professor Jun Sao just wrote a book. In that book, you will see different formulas to calculate such sample size. Yeah, such sample size. Yeah, if you one day you see right now you choose our program, it means you have a big chance to become a data scientist in the future. So in the future, when you have to deal with the specialist, right? So one thing you have to do is to help them to calculate the sample size. I remember 10 years ago, when I started my collaboration with the eye specialist in Hong Kong U. So my major work is to calculate the sample size for their trials, RCT, and then later help them defense with the reviewers. So if you calculate sample size, yeah, you may refer to Professor Jun Sao and Hans Wang's book. Yeah, very useful. Okay, and also there are many softwares that will help you to calculate the sample size. Yeah, this is a very important thing in clinical trials. Next one here, when you have such an experimental planning, next one, you will have the population. So in the population, you consider like your group A, group B, like the some random assignments. Then here, like for such group A and group B, it means that, yeah, like you have the treatment and you would have the group. And then it comes out something like we call it observation period. Here it covers the lateral fluctuation, and then here like you will have some proportion, yeah, for each group. And then like the formula here, yeah, you may use the lower volatility hypothesis and the sample size formula to calculate. Here you have to check what is your novel volatility and which statistic you would adopt and what kind of distribution it will follow. And then based on that, you then calculate your sample size. Yeah, so here we can summarize. This is the hypothesis and statistical test. This is your null hypothesis, and then here comes out some volatility one. Attention for this volatility one, because you use PA, PB not equal to each other, that means here you use the two-sided test, right? But if you simply do something, for example, you say like PA greater than PB or etc., that means you actually have a one-sided test. Yeah, and then here, for such a situation, we have the pooled proportion. So what does pooled proportion mean? Pooled proportion, that means if you assume these two are the same, identical, right? Then you just combine two samples together. So for the combined sample under your lower hypothesis, so here you can calculate something, but for the alternative one, so you would use another one. So finally, here you can calculate the standard error. Once you have the standard error, next one, using the Z test, so here PA minus PB, and then here the standard error in this way, you then have the confidence interval. Yeah, just here. Maybe later we can assign like one such assignment for you and a tutorial to practice. Okay, so this is about some hypothesis and statistical test. And here you can see more things. Yeah, in such a situation, you can see if you calculate the p-value, usually such p-value means what? P-value means the probability you have a test statistic. Yeah, remember, such a test statistic means this would be a function of your random sample, right? So when you have this one, yeah, and here you use like sorry, here, no, this one. Yeah, so that means here you use the attention, it just writes lowercase. Yeah, you see my writing here? So this is a p-value. So how do you understand? You say you have a test statistic, but for this lowercase x, it means what? This one just means your observed value. Yeah, this is observed value, or just like the realization. We call it the realization of the test statistic. See? So you calculate such a probability. Here you like, yeah, you know for Tx, you must calculate its CDF, PDF, or any distribution function. So through it, if you calculate this, so this is a p-value. If this p-value is less than alpha, you know, alpha is a pre-assigned level of significance. It's a very small value, right? Usually like a 0.05. But right now, like the p-value you calculate is less than it. That means what? That means such an event is rarely occurs, right? So if such events rarely occurs, then you have to reject your null hypothesis, right? So here, so p-value less than alpha. And also you may consider p-value greater than or equal to alpha. Here, that means you would fail to reject H lot. Why? Because such event occurs has a large chance to happen. Yeah, simply just like in this way. If you consider a p-value smaller, that means the probability it occurs just fall into the two ends. And here the probability is very small, right? So this is p-value methods. Yeah, but you also know that several years ago, people do not like p-value method. They say this is only a purely mathematical game. But yeah, you have to admit sometimes there would be a gap between mathematical derivation and the empirical situation. So to prevent mathematically ridiculous situation, what you can do is what? You just put your empirical experience in 2 to reduce the some ridiculous thing to occur. Yeah, so this is about the summary, hypothesis, and statistical test. If you are very familiar with these parts, then you will feel you may relax in the next few weeks. But if you feel this is quite abstract, then these several weeks you should pay high attention. Yeah, because we will give more details on confidence interval and hypothesis test. And then next one, you can see compare like the estimated proportion, calculates the p-value, and you may have confidence interval or some other business impacts. And finally, you do some decision. Here, decision is to choose a better version to continue or stop the test. So here you must understand for a data scientist, can we do decision? No, we just provide evidence, right? Yeah, if people give us data, we may try to build up a procedure to see what we can find from that data. And then you tell some results. But finally, when you make a decision, it relies on the party who assign you the task, right? For example, if the pre-assigned level of significance alpha, if this one is almost like 0.1, that means the requirement is not strict, right? So in this way, that means, yeah, in higher probability, you may accept something, but if such a level of significance would be 0.01, that means what people would be very strict, like the food safety, right? In such a thing, then the decision would be quite different. So decision made by others, but for us, we provide evidence from a scientific way. Next one, I just want to make some comparison between frequent test and Bayesian inference. So frequent test and Bayesian inference were almost half-half. So roughly, you may understand in this way. For frequent tests, usually they can build up beautiful theory, but in computing, seems they have shortage. But for Bayesian, here people used to have some ways to do iteration computing, updating. Yeah, but in theory, it seems a bit of hard to build. Let's just check inside. Here we have some comparison from the parameter review. For frequent test, here the parameter would be fixed but unknown. But for Bayesian paradigm, yeah, so here we take parameter as a random variable, and we even have some prior information. For example, yeah, you see my memory is not good, so sometimes I would lost my things. So then one question like, yeah, this is this pencil, right? iPad pencil. So you may say the iPad pencil is missing again. What would be the probability? So here you may have some prior information. For example, you say, oh, Catherine, in the past 3 weeks, you taught us, and 2 times you forgot to take your iPad pencil. So here seems like there would be some prior information. I have 66% or so possibility to lose my iPad pencil, right? So this is some prior information. But for frequent test, we fix that one, right? Fix unknown, but then we try to find some approximation. And the next one, the uncertainty source. This is pretty important. So why do we have data science? Because there is uncertainty. But for uncertainty, for frequent test, they just sampling variability and repeated experiments. So in that way, like usually they assume there would be x1 to xm. There would be some random sample. They would be identically independent distributed, right? Yeah, here I say IID. Yeah. But for Bayesian, that means you would have what? Prior uncertainty, right? Usually, for example, you use some pi t theta. Yeah, theta is drawn from pi t. Theta is your parameter. Yeah, you know theta here, theta unknown, right? Theta unknown, you try to give some approximation, and such approximation may be denoted by your data, right? Yeah. Yeah, so this is one. But here for Bayesian, here you will have a prior uncertainty, and then you have the data variability, right? So that means words usually I would say you have prior information once you are given a data plus likelihood, you then do update, and the prior becomes posterior. For your posterior, it becomes a new prior. Yeah, yeah, you may remember me. I can upload a paper for you from a Nature, um, just like a late a Nature subjournal. Yeah, it's not about Nature review. There it just introduced the how Bayesian paradigm works. Yeah. Okay. Next one is about the interval. For interval here, attention. Under frequent test, people would like to use CI, confidence interval, to tell things. And here CI just means a long, this one tells you is a long proportion of interval containing the true parameter, right? This is confidence interval. However, for Bayesian here, people use the CRI. CR just means credential interval. So this one tells you the posterior probability of parameter lying in the interval. Yeah. So these two are different. Okay. And next one, the update mechanism. So for Bayesian frequent test here, we have the Bayesian theorem, prior, posterior, and then update. Anyhow, you can just remember it's like data, then plus likelihood, right? So here prior, yeah, this is prior, then this one derived posterior. Yeah, and then posterior becomes prior again, you update this, right? But for frequent test methods here, no explicit, yeah, there's no explicit, you just use the sampling distribution. So here for sampling distribution, if you refer to what I uploaded about the fundamental probability, you will find we actually have a figure to show the possible relationship. For example, we have some chi-square distribution with a degree of freedom m, and also we have t distribution with a degree of freedom m, and also we have some f distribution with a degree of freedom nm. So here we actually have three famous sampling distribution. And for these three sampling distribution, you can use a normal distribution. For example, if I denote bias, and also like if we have like x1 to xm, through such x1 to xm, you can derive the chi-square distribution, and also you may derive the Tn and Fnm. Yeah. If you forget this, you can actually go to Blackboards and go to the contents about the fundamental and the bivariate random variable introduction. There, we have a 2-page supplementary. Over there, I just show you like from normal how you derive to any place. Okay, so here is the one. Next one, I just want to tell the typical workflow. So for the typical workflow, let's check the frequent test first. For a frequent test, specify the null and volatility hypothesis first. Choose a tester statistic. So here for this test statistic, I just write in this way, right? But for this one, you can write by T. Yeah, this is one that we have. And then next one, you have to derive the distribution, right? Yeah, this one is extremely important. Why? Yeah, if you cannot do that, you can do nothing. Yeah, remember, for example, like your p-value, right? Your p-value equals probability t is less than, yeah, here's the one that we have. So it means what? It means that you actually try to do something like here, t and x, right? Yeah, and df. So this is where you calculate your p-value. So that means what? That means here, if you cannot know this distribution, then you can do nothing, right? So that's why here we say this is extremely important. Yeah, we call this one sometimes the Lauer distribution, 零分布. Yeah, Lauer distribution. Similarly, like such a distribution under the volatility, we call it the 对立分布. Yeah. So, and then you compute the p-value, and then here you have the critical region. For example, one would reject or fail to reject each lot based on the significance level. That means what? That means here when you have some hypothesis test, you would have what? You would have a data set x1 to xn. So it would be follow some distribution. For example, I just write it this way. So this is your random sample. And also you have a pre-assigned level of significance. Usually, like it would be some type 1 error probability. Yeah, so for this one, we call here, we should have some critical region. So what is a critical region? You may say this one is a rejection region, 否定域, yeah. And then construct a confidence interval using the estimator and its standard error. Yeah, so this is the way that we do the frequent test. Next one, let's go to Bayesian. For the Bayesian, here you can see specify a prior distribution for the parameter, and then collect data, construct likelihood. See the one? Here is the one I just write. I would like to write again. Here you say data plus likelihood, right? And here is the prior. So then you update, then you have the posterior, right? And for this posterior, then it becomes prior again. And then you just update it. Yeah, update this. So this is the Bayesian method. Yeah, this one does make sense. Yeah, because you use your known experience and you continue updates, and then you understand the world, the society, and the people. Yeah, so here you can see summarize the posterior with like a point estimator, like a posterior mean or median, and credible interval. Attention, credible interval, that's the confidence interval. And next one, posterior probability of hypothesis. Yeah, so this is two different ways. Yeah, I'm not sure whether you are familiar with this or not. Yeah, but whatever, we will just expand it one by one. So next one, I just introduced the sampling data, sampling methods. For sampling methods, yeah, so just now I introduced like a chi-square TF distribution. Usually, if you are an undergraduate student in statistics, you would learn that. If not, you can go to Blackboard to find the supplements I sent. Here we want to introduce you more some other probability sampling. And here, attention, here we have a comparison. The first one, simple random sampling. 简单随机抽样. So here we can see the characteristic. Every member has an equal chance and also is a lower chance of selection, and it's completely random. And here we have some suitable scenarios when the population is homogeneous, 同质的, and a full list of members is available. Yeah. So for example, like for our classroom, yeah, like war girl students would be homogeneous, or boy students would be homogeneous. If we want to investigate your consuming pattern, so boys and girls would be quite different, right? Yeah, for example, for a boy, yeah, he may just wear a t-shirt Monday to Friday, just the same. But for girls, you never see such situation. Then that means the consuming pattern will be also different. But if we try to sampling from the whole class, that means what? That means it can indicate like 2025, the students who entered into PolyU and into such FCMS, so what would be some common things? The next one is about the systematic sampling. For such systematic sampling, you select every case element after a random start. And this one just means it's simple to implement. And here you have to care about what would be the scenario in the situation that the population is moderate and you want to have a even spread of samples. Yeah, so then you use the systematic sampling. The next one is very important and very useful. We call it the stratified sampling. You see, for U.S. president selection, each time people would do some survey and do some more things to do prediction. Then the sampling, they would use the stratified sampling. Here you can see the population divided into different strata and then sample randomly within each stratum and ensure the subgroup representation. So here you stratify the sample because you want your sample would be representative. So that means it would be a small model of a large model, right? So here when the population has a clear subgroups like gender, region, weight, etc. Yeah. Next one is about cluster sampling. For cluster sampling here, randomly select clusters, then sample all or part of members within them. For example, just now when I say something, I say if I try to draw from your students, I say I cluster by gender, right? You have girl students, boy students, and I think within each cluster, the distribution would be the same. Yeah. So when the population is geographically dispersed, cluster lists are available. You can do. Next one, multi-stage sampling. For this multi-stage sampling, here sampling done in multiple stages. And then you have to combine several methods. So this one is suitable for what? For large-scale surveys where step-by-step laddering is more practical. Yeah, so this is about sampling. For sampling here, we still want to mention more. One thing is about the stratified sampling and the cluster sampling. There would be some slight difference. You can refer to the table. Next one, we want to mention some long probability sampling. This one just means words. The probability selection is unknown and not all numbers are guaranteed a chance to be selected. So in this way, usually the disadvantage would be worse. There would be higher risk of bias. Yeah, look at this one, long probability sampling methods. For the methods, we have the convenience sampling. So this one means what? You select the easiest members to reach, quick and inexpensive. But then here the primary studies where the time resources are limited. That means it is just for some experience, but it means worse, it may not be reliable, right? And also you would have something like the judgmental or purposive sampling. So this one, the researchers choose members based on expertise or judgment. Yeah, this one sometimes, I mean, in some special case would be suitable. For example, if I try to apply promotion, so the department would choose referees, right? Here you choose a referee randomly, and the referee said, "Oh, Catherine, good," so you give promotion. But the referee says not good, then you give no promotion. So this is a judgmental and purposive sampling, right? So in such a way, the specialized research where specific expertise or traits are needed, right? So that means when the department has to decide who will be my referee, then they have to decide that should be some like fair people and with the high standard, yeah, just eligible to judge my expertise. Next one is about the quota sampling. So this one just ensures certain group proportions without random selection. So for quota sampling, this one just this one just tells you that like you have to decide the quota. Once the quota is satisfied, then yeah, game is over. So here it means words when the subgroup representation is needed, but random selection is impractical. Yeah, in situation you would do. Next one is about the slow ball sampling, 滚雪球. Yeah, this one is a very just a typical long probability sampling methods. And in such situation, the participants recruits other participants. So in such a situation, it can grow sample iteratively. For example, like you can build a website, ask people to do something, like you give them some incentive, right? But here is a hard to reach or hidden populations, like a rare disease, and then you choose such a way, okay? Yeah, so this is several sampling methods. Next one, I would like to introduce the sampling errors and the biases. So here, errors and biases are two concepts that you will encounter often. For error, error means words. Error just like if you have some like estimator, right? Yeah, you have an estimator and you have the two, so their difference would be your error. But for buyers, when we mention the buyers, that means here for your estimator, you calculate the average and then deduct the two. So this one comes out the buyers. If this bias, like if this one 0, then we would say it is unbiased, right? Unbiased means accuracy, and the error smaller means accuracy, right? So errors and biases can arise at a different stage of a study. Usually, it will affect attention the accuracy and the validity of results. So they are often categorized as what? Like the systematic bias consistently skew results in one direction. Yeah, so this one should be careful. So usually we hope that the systematic unbiased, right? And next one, random errors. So this one just tells you fluctuates unprecisely and average out with large sample size. Yeah, so here we can some in more details. Here is a systematic biases. For example, we have the sampling bias, the survivorship bias, selection bias, and the wrong response bias. For each of them, here comes out the meaning and the reason and the impacts. Let's see the meaning first. For sampling bias, here each one, this one tells you the sample is not representative. Sampling bias, not representative. Yeah, this is one. And then for survivorship bias, only cases that pass the selection filter are analyzed. So this one ignores the rest, right? Yeah, for example, like you student here, if we say, yeah, for example, if we say some study just investigated among you guys and we have the conclusion, but it may not represent the domestic China postgraduate status. Why? So if you go to Hong Kong, that means you have to pay the tuition, right? That means your family and the parents actually need to be affordable for the money. Yeah. So in such a situation, that means, yeah, you can represent the families who should be over the average. I mean the economic status, right? So here you should be careful about this one. Next one, selection bias. Here the certain individuals are more likely to be included in the study. For example, if you just study in some people what kind of skirt people would wear, so possibly girls would be drawn, right? But for boys, they may have less interest. Next one, wrong response bias. This one just means wrong participants differ systematically from the participants. Yeah, here because when you sampling, there would be different characteristics. Then you see there would be different impacts. And here the impacts means some bad impacts. For example, the first one leads to the biased estimates that do not generalize to the population. The next one would generate the overestimation of the success rates. The second one just the distort causal inference and the generalization, selection bias. So here, for generalization and causal inference are two things of people's interests. And the first one, estimate is skewed towards the view of the respondents. Like the example I mentioned, in history of United States, the president selection, there are only 2 times the prediction failed. Yeah, the reason just because like the response population has some bias. Yeah. Okay. Here for examples, I do not mention here. Yeah, but you guys should be careful. Yeah, we have low midterm, but in the final examination, I would set one question like you have multiple choices. So for this kind of multiple choice question, how do I set this? It comes from our teaching notes. For example, I may set a question about for some example, you see it belongs to what kind of buyers. So then you have to do one, right? Yeah, that would be one problem. Yeah. Next one, I just want to introduce the random errors. Oh, let's stop, take a break, and 30 we go back. Yeah, thank you.